Okay, in this video, I want to start by showing two very basic ciphers. One called the Caesar cipher and one called an affine cipher, which are used to encrypt messages in a very basic way. You don't need much math here at all. It's just a little bit of math. So I'm going to explain the math behind these two ciphers. So first, we start off by assigning to each letter of the alphabet a number. So A is 0, B is 1, C is 2, up until Z equals 25. Okay? Now, with these numbers 0 through 25, we can do addition, subtraction, and multiplication. Okay? But it's a little bit different than usual addition and multiplication. Okay, so addition and multiplication. How can we do this? Well, for many numbers, it's going to be the exact same thing as always. So, for example, 3 plus 5 is going to be 8. Okay, but what happens if we do, for example, 23 plus 5? Okay, this is 28. Okay, so if we look up here, we go 23 plus 1 is 24, plus 2 is 25. But instead of going to 26, we're going to start over at A, at 0. So plus 23 plus 2 is 25. Plus 3, we're going to go all the way over here. Then plus 4 and plus 5. Okay? So this is going to be 2. Okay? So it's basically some kind of cyclic addition. Okay? Now if we have this, so for example, if we have 28 equals 2, if we subtract 2 from each side, then we basically are getting that 26 is equal to 0. Okay? So this is called arithmetic mod 26, modulo 26. Whenever you see the name mod, it's basically because we're sweeping all that under the rug. 26 is swept under the rug and it's equal to 0 now. Okay? So for example, 13 times 2 is going to be 26 is equal to 0. Okay? We have 15 plus 15 is equal to 30, which is equal to 26 plus 4, which is equal to 0 plus 4, which is just 4. Let's see, what about 12 times 5? This is 60, which is just 26 times 2, which is 52, plus 8. 26 is 0, so this is just going to be 8. Okay, so we have this new addition and multiplication where we're considering 26 equal to 0. So this is arithmetic mod 26. And actually you can do this in Google. If you do any operation and you just put mod 26 in Google, then it's going to calculate it immediately. Okay. Okay, so let's do the first kind of cipher, which is called the Caesar cipher. Okay, so what we're going to do with the Caesar cipher is we're going to start off with a key, which is just going to be a number between 0 and 25. Okay, let's say for our example, let's take the key to be equal to, 5. Okay, so let's take, for example, a message hello. Okay, first of all, we're going to translate this into numbers. Okay, so using the chart above. So H is equal to 7 on this chart. So it's going to be 7. E is equal to 4. L is equal to 11. And O is equal to 14. Okay, so this is going to be 7, 4, 11, 11, 14. Okay, that's just, we're not really encrypting anything here. We're just translating a message into numbers. But now the Caesar cipher, what it does is you add the key to each number. Add the key. Okay, but with this new addition where 26 is equal to 0. Okay, so in this case, if the key is 5, then 7, so we're going to add 5. Okay, so 7 turns into 12, 4 turns into 9, 11 turns into 16, 11 turns into 16, and 14 turns into 19. Okay, then we just translate this back into letters. 12, 9, 16, 9. So let's see, 12 is M. Okay, so we're going to get M. I'm going to write in capital letters the encrypted message, and in undercase the original message. It's just to have things organized. You don't need to do it. Okay, so 12 is M, 9, 16, 19. So 9 is J, 16 is Q, and then 19 is T. So we're going to have J, Q, Q, T. Okay, so that would be my encrypted message. So if I, for example, want to send this to a friend, I send him MJQQT. Of course, he's going to need the key beforehand to be able to understand what the original message is. So how would my friend do it? So, for example, if my friend gets this message, MJQQT, he has to have the key. Let's say he knows that I use the key 5 to encrypt this. Well, first of all, he just translate this into numbers again. So it's going to be 12, 9, 16, 16, 19. And then to undo what I did, all he's going to have to do is to subtract 5. Okay, so then subtract 5. So in order to crack the code, he just has to undo what I did to get the encrypted message. He's going to subtract 5. So 12 minus 5 is 7. 9 minus 5 is 4. 16 minus 5 is 11. 19 minus 5 is 14, which, when we translate this back to letters, is HELLO. Okay? So, in general, actually here it'd be subtract the key, actually. This is the general way of doing it. Subtract the key. Okay, so if you want to send an encrypted message using the Caesar cipher to a friend, first of all, you have to, beforehand, you have to talk with your friend and say, okay, let's set the key equal to, I don't know, 20, any number you want. And then you can send all the messages you want. The one who sends the message encrypts it with 20, and the one who receives the message then undoes that by subtracting 20. Okay, so this is the Caesar cipher. It's very easy to hack, basically. For example, if I receive this not knowing what the key is, but I know that they use the Caesar cipher to ciphers to encode this, then all I need to do is to subtract all numbers between 0 and 25, and eventually one of the messages will make sense. Okay, so there are 26 possibilities, essentially. It's not that hard to do. Okay, but it's a fun little cipher. And history says that Caesar used this cipher to send messages when he was at war. So he'd tell his troops what to do, but using a Caesar cipher so that the enemy wouldn't know what he was saying. Okay. All right, let's see one that's a little bit more complicated, but it's the same principle. Basically turning a message into numbers, then to each of those numbers we're going to do a certain operation, and to receive other numbers, and then to each of those numbers we're going to turn those into letters again to get the encrypted message. Okay, so this one is going to be called an affine cipher. Okay, and so for the affine cipher, the key is a little bit different. So for the Caesar cipher, the key was just a number. For the affine cipher, the key is going to be a pair of numbers. Let's say A and B. Okay, where A and B numbers between 0 and 25. But I'm also going to ask something for A, something special. I want A needs to be invertible. Okay, what does invertible mean? Well, a number is invertible if there exists another number such that the product gives 1. Okay, so for example, with this new multiplication and this new addition, we have invertible numbers. So take, for example, 3. If I take 3 times 9, this is going to be equal to 27, which is just 26 plus 1. Which 26 is 0, so this is just 1. Okay, so in a sense, 9 is the inverse of 3. 9 could be thought of 3 to the negative 1, or it could be thought of as 1/3 if you want, okay, with this new multiplication. For example, if we take 11 times 19, okay, I don't know this off the top of my head, but I know that I did it beforehand. This gives 209, which is just 208 plus 1. Okay, and 208 is equal to 8 times 26. Okay, so since 26 is 0, this is just equal to 1. So 11 and 19, 11 is the inverse of 19, and 19 is the inverse of 11. Okay, and so what are the invertible elements here? The invertible numbers between 0 and 25 with this new multiplication and addition. Well, for example, 2 isn't invertible because 2 times 13 is 0. It's 26, which is 0. So if something gives product 0, you can prove, it's not hard to prove, that it can't be invertible. So the invertible elements, it's not hard to prove that invertible elements are exactly the odd numbers between 0 and 25, except for 13. Okay, 13 isn't invertible because 13 times 2 is 26, which is 0. But you can prove that all the other odd numbers are invertible. And this has to do, it's not that hard to prove, but it's because all the odd numbers except for 13, their greatest common divisor with 26 is 1. Okay, 13, the greatest common divisor between 13 and 26 is 13. Okay, but I don't need to get into that right now. Okay, so what I'm going to do is the key now for the affine cipher is a comma b, where a and b are any number between 0 and 25, and I'm going to ask for a to be invertible, which means in this case I want a to be any odd number except for 13. Okay, so how do I encrypt now? So encryption with in the affine cipher case, so we're going to if I have any, let's say that I have any x, not the letter x, let's say this is just any number. Then what I'm going to do to turn this into another number is I'm going to multiply by the first, by the invertible element of my key, and then I'm going to add b to it. Okay? So, example. So we're going to do hello again. Hello, first we change this into numbers. So H was 7, E is 4, L is 11, 11, and 14. And let's take our key. Let's take it to be 3, because we know 3 is invertible. And, I don't know, let's do 6. Okay? B can be any number. Okay, so what I'm going to do here, I'm going to multiply by 3, and then add 6. Okay? So, 7 times 3, so let's do the multiply by 3 first, plus, and then add 6. This is going to be equal to 21 plus 6. Okay, 21 plus 6 is 27, which is just equal to 1. 4 times 3 plus 6 is 12 plus 6 is 18. 11 times 3 plus 6, running out of space here, that's 33 plus 6, which is 39. Now 39, okay, so 39, but this is 26 plus 13. So this is just 13. Then I'm going to have to do it down here, 14 times 3 plus 6. Okay, 14 times 3, that's 28 plus 14. That's 42. Plus 6 is 48. But 48 is 26 plus 22. So this is just 22. Okay, so then my new numbers are 1, 18, 13, 13, okay, because remember 11 is repeated 2 times, that's the LL. 13, 13, and then 22. Okay, and now I translate this back into letters. 1 is B. Okay, then we have 18, 13, 22. Let's see. 18 is S. Okay, so it's S. 13 is N. S, N, N. And then 22 is W. S, N, N, W. Okay, and this is going to be my message that I send to a friend. And it's safe because no one knows what the key is, apparently. Okay, so that's the way we encrypt a message. Now, how is my friend going to decipher this? Okay, so how to decipher this using the key. Okay, so remember the key was 3, 6. So my friend receives this message, and what he has to do to see the original message is he has to undo what I did. So what did I do? I multiplied by 3 and I added 6. So what does he have to do to undo that? Well, first he has to subtract 6 and then divide by 3. Okay, so in general, if we have this, if A comma B is the key, then to decipher, we need to subtract B and then divide by A, okay? Division by A is a little bit different here, mod 26. I'm going to explain that in a second. Okay, so first, so let's say we have B, S, N, N, W. So first we're going to subtract B. So let's say in this case we're using the key 3, 6, as we did before. So first let's subtract 6. Okay, so B is, so here we have 1 minus 6. This is minus 5. Okay, so how do we get a number between 0 and 25? Well, this is the same thing as 26 minus 5, because 26 is 0. Okay, but this is the same thing as 21. Okay, then S is, let's see, S is 18. So we're going to do 18 minus 6, which is just 12. N is 13. 13 minus 6, which is just 7. Then 13 minus 6 again for the other N. And then W is 22. And then 22 minus 6 is just 16. Okay. So we subtract 6. That undoes the adding 6 that we did over here. Okay, but now how do we divide by 3? Okay, so that's the interesting thing here. We can't really divide by 3 in the sense that we're not going to use rational numbers here, but we can multiply by 9. Multiply by 9 undoes what we did when we multiplied by 3. If I multiply by 3 and then I multiply by 9, I'm just multiplying by 1 and I'm not doing anything. So division by 3 is just multiplying by 9. Okay, so now what I'm going to do is multiply by 9. And for this, I'm going to use Google. Okay, so the first one, 21 divided by 3 is 7. That's easy to see. But I'm going to do this multiplying by 9. So 21 times 9 is 189. Okay, so it's 21 times 9. It's 189. But I'm just going to use Google here. I'm going to put mod 26, which means I put equal to 0, any multiple of 26. And so this gives me 7. Okay, so I divide by 26 and it gives me remainder 7. Okay, which is basically, if you can see, 21 divided by 3 is 7. Okay, 12 divided by 3, the next one is 4. Okay, so it should give us 4. But let's do this using Google. So 12 times 9 is 108. Okay, so we get 108. And 108, if I do this in Google, mod 26, this just gives me 4. Okay, Then 7. See, 7 I can't visibly divide by 3 because it'd give me some kind of fraction, but that's where I can multiply by 9. So multiply 7 by 9, it gives me 63. Okay, and 63 mod 26 is 11. Okay, so that's my n. I'm going to add this again because n has to be repeated twice. This gives me 11. And then 16, I'm going to multiply by 9. So 16 times 9 is 144, which mod 26 is just 14. Okay, and so you can see now we translate this back to letters and we get H-E-L-L-O, our original message. Okay, so this is an affine cipher. This is a little bit more secure. It's not secure for computers. This is very easy to decipher using a computer. But by hand, this is a little more complicated because I believe there are 312 possible keys. Okay, so if you want to send a message to a friend in class, for example, using an affine cipher, unless someone gets a hold of the key, it's going to take them a while to figure it out because they're going to have to go through 312 different combinations to finally find out what you wrote. Okay, so these are two very nice, simple ciphers using a little bit of math, and they're fun to do, fun to play with these with friends, and fun to use for crypto challenges. So I hope this video was useful to you, and I hope to be doing more videos in the future. Thanks for watching.